we are going to start working on problem 70 from page 279. This is discussion 15. Okay, so we're given some vectors. I'll write those down. Okay, so here we have some vectors that were given in problem 70. 4I hat minus 3j 2k. Yep, and okay. So now it wants us to do this operation. Dot product of this vector that's the resultant of c minus b, right? So let's find c minus b first. C minus b. That's going to equal. So with vectors, we can just add them, right? So that's, we don't really have anything to worry about here. It's pretty straightforward. 4I hat minus 3j hat minus 2k hat. Right? 2j minus 4I plus 3j plus 2k. Okay, so we just add only in the direction, right? So like in only like we only subtract or add in the I hat, j hat, or k hat respectively. So 2 minus 4 hat, 2I hat. 2 plus 3 plus 5j hat. Negative 4, oh, there's, oh, that's it. And then plus 2k hat. Right, I was just reading it wrong. Okay, so that's c minus b. Now we take the dot product of that. C minus b. B. That's equal to a dotted with 2I hat plus 5j hat plus 2k hat. That's going to be, we just have a is just I, j, k. Dotted with, I'm just going to copy this. Okay, and likewise with dot products, we do the same thing as with arithmetic for vectors, right? So we only stick with the operation only goes in the same direction. So here we go, 2 times 1 I hat, that's going to be 2. And then we have plus 5 times 1 is 5. Plus 2 times 1 is 2. You sum that all up. I neglected to actually write down this negative sign. So I made the mistake of not writing that down here. So this needs to be put into all of this, right? Because this is negative 2 times 1, so that's actually there. So now we have these cancel, and this is equal to 5. So the answer to a dot c minus b is 5. And it's a scalar value because we're taking the dot product. So anytime we take a dot product, we end up with a scalar value. If we were taking the cross product, it would be a vector value, or just a vector. All right, next problem. Okay, so we're given a setup for problem 56. I've taken the time to draw it here. So we're told that a car is rolling down a track, and then it's going to go through this loop and come out the other side. And what we want to know is at what velocity can we get this thing to just barely make it through. So what is the minimum velocity that we can get it to just barely go through? So down here, through here, through. Okay, so how we want to look at this is we can consider, I drew this other diagram, at what velocity does the normal force up here go to 0? Not is 0, not how, at what point does it equal 0? At what point does it just barely go to 0, right? What's the limit? So, in other words, we have this car going around this track. Let's do like a ball. Okay, just to make the drawings easier. So this thing, as it's going around the track, as it's speeding around the track, is pushing into the track, right? And you're going to have a normal force pushing back from the track. Okay? So here, Once it gets to the top, we want it to just barely exist. So we want the limit of Fn goes to 0. So that what that means then, since the sum of the forces at any point along this loop, we know is going to be mv squared over r. That's our centripetal force, right? So we want the centripetal force to equal, it's always the sum of the normal force and the weight force in a situation like this. But now we just want it to only equal, mg. So that's what's going to happen. Because this is going to give us the minimum speed to where this thing can actually go through. This would actually be negative as well. So those cancel. So if this were any higher, so in order for this to increase, so this is going to be the very minimum speed that we can have, right? But for this thing to increase, we're actually going to have some normal force, right? And as it's moving faster, your normal force is going to be pushing harder off of the side of the track. So this thing will increase, right? And that would give you a larger velocity. But now we want the minimum velocity. So let's just solve for that. We have mv squared over r is equal to mg. That's going to give you v is equal to gr square root of. So that's a good start. Now, we want to know overall, we are asked to find what is this height here. So how high does this thing have to be in order for this to make it around the loop, right? That's actually what's being asked. So I jumped ahead a little bit and interpreted it right away that we're going to need some speed that's just going to barely make it around, and that's how I found this. So really what we're trying to find is this height. So how high does this thing have to go in order to give us that velocity? So we already have our minimum velocity. Okay, this is what it's got to be at the top. So now we can use conservation of energy, right? As usual. There's no need for the work energy theorem here because we don't have any friction. I think we have some in the next... Yeah, we have some in the next problems. But this one we don't have to worry about that yet. Okay, so we have KE initial plus U initial is equal to KE final plus U final for this car rolling around the track, right? So if we just take a look at our diagram again, here our initial kinetic energy is 0. We're just going to release this thing from rest. So now we have mg y initial, right? That's the height. That's what we're trying to find. So that's pretty convenient. So that's just going to be on the left side. So then this thing comes down, and then we're going to have some kinetic energy. We're going to have some kinetic energy up here where we have our minimum velocity, right? There's going to be a half mv squared with the v min. And then there's also going to be, since this thing is sitting at the top of the track, there's going to be some gravitational potential, which is going to be 1, 2r. So that would be mg 2r. This is mg yi. And then our kinetic is going to be half m v min squared, where v min is this value here. Okay, so let's write that out. Mg y initial is equal to half m, and v min was square root of gr, and if we square that, we just get gr, right? And then plus mg 2r. And then all we have to do is solve for this. So let's do that. So this cancels with both sides, right? So yi is equal to half r plus 2r, and that's going to equal, it's going to be 4 halves, right? So that's actually 5 halves r. That's the height. That's the minimum height that you can drop it from or release it from so that it's going to get all the way around the loop. Let's just write this out here for fun. 5 halves r. Okay, for the next problem, we have the same setup. So scroll back up here. I'm going to take this. We have this. All of this is the same, right? That's what it tells us in the problem. So this is, but the difference is this is no longer 56, it's 57. And the other difference is that at the end of the track, we have friction. So we're going to have this car is going to come roll through the loop, and then it's going to come to a stop because of the friction. So we'll consider this, we'll just call this part C, right? So this is C, this is B, and this is A. So now we could go through the trouble. We could say, okay, so we want to find energy A is equal to energy B is equal to energy C. But we can also just consider that we have an initial energy and we have a final energy over here, right? And we want to know what happens between here and here. Remember, there is rolling friction, so we're going to have to consider our work energy theorem in this case to see what is the change in the system energy, right? So what we would do is we take energy A at A plus work, right? And that's going to be energy C plus the change in internal energy. So we know here all we have is potential energy, so there is no work at this point. We do have some change in internal energy here. So we have, what was it? It was mgyi is equal to, excuse me, there's no, so let's look at this here. And when this thing is on the ground, there's no gravitational potential. It has rolled to a stop. That's the point that we're looking at. So there is no kinetic energy here. So this is going to be 0 plus mu k times the normal force times the distance, right? From our theorem, that's what we have. And also, our normal force here, there's no angle or anything, so this normal force is just going to be pointing in the upwards direction, and it's going to equal the weight force, right? Otherwise, it would be jumping off of the track in some way or breaking through the ground. So that's what we're left with. I'll just leave those up. So that gives us this. mgyi is equal to mu k mg dot s. Okay, and if we look at both sides here, we can get rid of mg. Now we have yi is equal to mu k dot s. We already know what yi is. We found that in the last problem. It was what 5 halves r, right? So now we have 5 halves r times 1 over mu k is equal to s. We want to know what is the distance that this thing has traveled along the horizontal track. Given values, and we're given values in the problem. R is equal to 0.45 meters, and mu k is equal to 0.30, right? We'll say that. So now we have 5 halves times 0.45, 1 over 0.3. That's going to give us our distance. Let's plug that into the calculator. It gives us a value of 3.75 meters. That's how long the thing rolls. Okay. So number 84, we have Sean, and he rides a skateboard at a local skate park. Okay, we're given a diagram. So he's dropping in. He's dropping into like a half pipe. It's not quite a half pipe. It's kind of weird. He's dropping in anyway, and it goes up. There's a little hill, and then he rolls down the hill, and there's friction. So let's draw this. Okay, so we have Sean on his skateboard. He's dropping into this thing. He's gonna go up. He's gonna go down the hill. We're asked to find the speed at this point. I'll call it A. Then he's gonna come up this hill here. We're asked to find what is his speed here at point B. And then he's going to go, obviously, we're hoping he has enough momentum to continue down this slope. And we are asked to find something. What is it? Oh, change in thermal energy of the board rider track system. So we're asked to find the change in thermal energy down here. So we're going to need to use the work energy theorem here. So here we can use conservation of energy. Pretty straightforward. Here we can also use conservation of energy. So we find this speed here, and then we use it again to find this speed here. Then we use our work energy theorem here to find what is the change in thermal energy. And then we also want to know what is his speed as he reaches the bottom. Okay, so let's get started. So we're going to say this is our potential, our gravitational potential is mgh, right? So that's mg times 12 meters. What is m? M is given, I believe it is 45 kilograms. So let's just write that out as well. Why not? 45 kilograms times g. Okay, and then at the bottom of this ramp here, there's our gravitational potential goes away. These are all, I didn't draw it exactly to scale the way it is in the book, but if you look at the book, this is supposed to be pretty much, the ramp is at the bottom. So it's supposed to look something like that. But my drawing's a little funky. Alright, so the point is, gravitational potential goes away. We're only left with half mv squared, and we want to know what is v. No problem. So then we have v 2 times 12 times g. Right, so that's going to give us square root of 24 times g. So that is going to give us 15.34 meters per second. Okay, that's part A. Now B, we are asked to find, let's double check this, we are asked to find the speed at the top. So we have a speed here, he's going to go up, we're going to have a gravitational potential as well, and we're going to have kinetic energy. So we need to find the speed using both of those. So what I'm saying is we start with this kinetic energy, we have kinetic and potential at the top. Okay, so now we have 1/2 m times 15.34. Okay, and then we have, let's see what else we got. We got mgh is, so it's going to be m times 8 meters, mg times 8 meters, and then it's going to be another 1/2 mv squared. We'll call this vb squared, okay? So we just solve for vb. No big deal. Let's do that. Well, let's get rid of these m's. All we have to do is plug this stuff in. Minus g times 8. This is all times 2. And then there's a square root. So you could just plug it in directly like that, which is what I'm going to do, and that's going to give me an answer of, that gives us 8.852, we'll say, meters per second, right? And notice that at the bottom of the hill we had 15.34 meters per second, and at the top of the hill we had 8.852 meters per second. So we went down by quite a bit, okay? Not quite half, but it's close, right? So it goes down, it goes super fast, then it comes up, we lose quite a bit of momentum climbing this hill. That makes sense, so I'm happy with that answer. Let's move on. So C, we want to find the change in the thermal energy of the board rider track system. Okay. We can just plug in from our work energy theorem, right? Internal energy. This is also, we could just call this the thermal energy. That is an acceptable way to do this. So here we have change in the thermal energy is going to equal, what do we have? We had some frictional force times the distance, and we're told that the frictional force produced has a magnitude of 120 newtons. All right, and also note that we're just traveling a distance of 18 meters. We're just going right down. So we don't count this because it's not gravitational potential. We actually are talking about the distance traveled along the ramp is 18 meters. So we just multiply that, 18 meters. Our units come out to be Newton meters, which is going to be something in joules. Okay, and that multiply that together, we get 2160. So we say that the total change is 2160 joules. That's pretty straightforward. All right, and then for the next part, we're asked to find what is the speed when he reaches the bottom when he reaches the very bottom of the 18 meter ramp part. So as he's traveling down here, how fast is he going at this point? So I imagine he'll gain some speed, but it's not going to be nearly as much as we had over here. That's my guess. I don't know, but let's figure that out. Okay, so we know what the change in the thermal energy is going to be. So we're going to want to use the work energy theorem here, right? As I had mentioned before, we have a kinetic and a potential energy happening here. That he's in motion and he's got some gravitational potential at the top. Okay, travels down. There's not going to be any gravitational potential here at the bottom, but there will be some kinetic energy. So let's plug that stuff in. So at the top we had, let's see, what was his speed? 15? Nope, that's wrong. It was, oh, here it is. This is the speed that we want. 8.852. Right, that's squared. So that's our kinetic energy at the top, right? This is the initial kinetic energy plus mg times 8 meters, right? And this is going to equal, and then we have, our theorem gives us plus work, but we've already calculated what's going on over here, so we're just going to kind of leave it. Oh, plus there was no friction leading up to that point. So let's just go straight into the next part, and we have no gravitational potential, but we do have a kinetic energy, so we're going to have half mv squared. Okay, and then our change in the thermal energy, we calculated already, 2160 joules. Okay, and so now we want to know what the speed is. We'll call this VC, and we just solved for VC. So let's do that. So we have half mv squared is equal to half m, call this 8.852 squared plus mg 8 minus 2160, right? And then so we take 2 over m, and then we take the square root of all that. That's going to give us VC. So plugging in 45 kilograms for m in each of these places, and 9.81 meters per second squared for g, we end up with a value of 11.8078, or let's just say it's going to be 11.81 meters per second. So that's how fast he's going at the bottom of the ramp. Yeah, and that makes sense, right? So look at this. We drop into the ramp. We're going this speed, 15 meters per second at the bottom, and then we go up the ramp. We're going around 8-9 meters per second, and then we go back down the hill. There is some friction. We're not going super fast, but we end up picking up some speed. So we go 11.81 meters per second. So it's fast, slow, and then a little faster, medium speed, right? And that makes perfect sense given all of the conditions. So that's good. So next problem is problem 10, page 300. Let's see. We are given a velocity for a 10 kilogram object, and it's written on page 300. I'm not going to read it out loud. I'm going to write it down. And we're asked, what is the net force on the object as a function of time? Okay. This is actually, in my opinion, relatively straightforward. So if you know what to look for, okay, so here, I'll just write this down. So mass is equal to 10 kilograms. Velocity is equal to 5t squared I hat minus all this 7t plus 2t cubed j hat. Right? And we're asked to find the net force. Okay, well, let's recall Isaac Newton, right? F is equal to ma, where m is your mass, right? And a is the derivative of your velocity with respect to time. And we're told in the problem it also states that t is in seconds, so that means that units of velocity is meters per second. So what this is telling me is that we need to find the time derivative of this vector and then multiply it by 10 kilograms. So let's do that. So let's just go 10 kilograms times 5t squared. We're going to 10t I hat minus 7 plus 6t j hat. Net force is going to be, well, we have 100 newtons in the I hat direction. Then we have minus, let's just say 70 plus 60 times time. It's still a function of time in the j hat direction. Oops, I forgot to write down squared here. It's my fault. So this was cubed. So just to point out my what I forgot to write down. So this goes away, right? In the derivative, we just end up with 7. This goes 3 times 2 and then t squared. Okay, and that's your net force. Okay, so the next part of the problem, part B, it says what is the momentum of the object when t is equal to 15 seconds. Okay, so our velocity is a function of time, so we're going to need to plug 15 seconds into each of these. Also, just to recall that we need to recall that momentum in general is mass times velocity. Okay, so we're going to take 10 kilograms times our velocity function, where t is equal to 15 seconds. Okay, so we just plug it in and go from there. So what do we have? We have 5 times 15 squared I hat. Let's do this. That way we can see. Okay, and then what do we have? 7 times 15 plus 2 times 15 cubed j hat. Okay, plug this into a calculator. So I plugged that in, and what I got were some pretty high values, but I mean, momentum is mv, our mass is 10 kilograms, and I mean, our velocity function is rather outrageous. I mean, this is a cubic function for time, right? And it's traveling at 15 seconds. So if this thing is left unchecked, I mean, we're gonna have some pretty crazy momenta here. So when I found these answers, what I did was I was like, that seems high. So what does that equal? So if you have an SUV traveling at about 100 miles per hour, that's how much momentum you're going to have in this direction. So it seems like a lot, but that's what we're given, and that's what we get. So that means also then, if you just find this, I think this thing was going at like 6,800 meters per second for this. Like that's really fast. Translates to like 15,000 miles per hour or something like that. So this must be an asteroid, like in orbit. I think the ISS in orbit around the Earth is traveling at like 17,000 miles per hour. So it's not unreasonable if this thing is in space, or if it's a rocket and we're shooting it up to space or something. We can get to those speeds. So anyway, that's what we get. Thanks.